Yes, yes, sir.
Okay, okay, fine. So we are now talking about Galerkin finite element method for the Navier-Stokes equation, and we'll be talking about discretization of computational domain in M linear or quadratic elements with total n nodes. Approximation of dependent variables. We are having the three dependent variables u, v, and theta. Three dependent variables u, v, and theta, and nodal variables are ui, vi, and theta. This is the typical element local nodes. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9. And here the basis functions, as I discussed earlier, a polynomial of xy satisfying Kronecker delta properties is a Lagrange polynomial. And error is orthogonal to the basis function. And here u is the nodal variables. You could be capital U, capital V, and theta. And you can have each node. You can have the three residuals. You can note. So that means you have 25 nodes. You will get 75 algebraic equations. If you have 25 nodes, you get 75 algebraic equations because you have three unknowns and three equations: two Navier-Stokes equation and one energy balance equation. So the mesh generation or the irregular domains we can actually have, and more elements or higher order elements in regions of larger gradients we prefer, and sometimes we have triangular nodes. I'll be discussing how the generic ways we can actually use the finite element meshes. In fact, I have got my own algorithm. If you follow, and you can have very complicated meshes. For example, if you want to develop a mesh within a snake, the snake has got very kind of flexible structure. In fact, with my kind of meshing configuration, we can develop meshes within the snakes, within the spider net, and so on. Even we can actually generate mesh within aerofoil bodies and something. So this is the mapping, isoparametric mapping actually we have, and this is the now we are actually talking about more details of finite element. First part I have given general introduction, and now we are talking about the evaluation of integrals. We have seen the integrals in the first part, and if you want to know how to evaluate the integrals, and that could be always double integrals and so on. And for any irregular domain, we have to evaluate the integral. That is not straightforward, and that you have to handle with all formal algorithms. If you look at here in your extreme left, I have given the biquadratic basis function. You can see that the basis functions are written in terms of z and eta. So here we introduce the coordinate system z and eta. What are they? If you look at x and y coordinate, the element is not non-square element, but this element has been converted to a square element in z eta coordinate, and this is called as isoparametric mapping. So here we say that isoparametric mapping, and this is the way. So isoparametric mapping, that mapping actually what it uses, the whatever basis function we have used for the velocity and temperature, the same basis function you have to use for x and y to generate this type of mesh. And in that case, advantage is we all know how to do the two-dimensional integration, how to do a double integral, and double integral in square domain can be easily done. So any irregular domains like this, even with the curved side, we can have curved side also. So that can be mapped in a straight line boundary square domain, and we can do all calculations, all integral evaluations, and entire calculations can be done. Entire residuals, what we have done, we have got it. That can be done in this square domain to obtain set of nonlinear algebraic equation. So node numbering, global versus local, same node numbering we can use. that we have discussed, the same node numbering, and node number will not change, but only thing is number of variables will be changed. I think we still remember this, so this I wanted to have recap. Now I will go to the construction of residual. If you see, at each node there are 3 unknowns and 3 residuals. There are 3 unknowns and 3 residuals, as I discussed. So there are 25 variables, 25 nodes, and we have 75 variables. Now the arrangement, how to do the arrangement? As I told that in the first part of lecture, that the costliest part is solver, and solver has to be the banded solver. So that means we have got 3 differential equations: x component of velocity, y component of velocity, and temperature. One way to arrange the residual, I will take all x component of velocity, do the residual for all 25 nodes. Then I will take v component of residual, do all the things for 25 nodes. Then I will do all temperature for 25 nodes. Another option is I will take the first node, finish off all u, v, and theta. Then I'll go to the second node, finish off u, v, and theta, and so on. So a second way, if you do, you get the bandwidth lower than the first approach, and we need to have lower bandwidth of the banded matrix so that you can have faster solver designed for your finite element algorithm. So if in that case we can see that there are solution variables. So you have a total 75 solution variables, but for the first node the global variables are u1, b1, theta 1. That corresponds to the solution, because remember that you have the nonlinear algebraic equation at the end, and the Jacobian matrix size will be 75 by 75. Jacobian will not know what is for u, what is for v, what is for theta. It will have the global package for you. It will have global package, but you will know only which variable of u will correspond to what velocity of what is the what small u variable will be corresponding to your velocity vector. So small u1 is nothing but capital U1. So small u2, you can say, okay, this is my y component of velocity of the first node. u3 is my temperature for the first node. For example, you have the u5, which is the y component of velocity of the second node. So that mapping you have, but once your computer program is solved as a overall package. So similarly for the global residual, we have the local residuals. So similarly, one can actually have the construction of so this actually first I talked about the generalized principle, and then we have the internal nodes. We can have that one internal node here, and we can have the shear node contribution from the from more than one elements. We can see that we have 1, 2, 3, 4, 5, 6, 7, 8, and we can see that this 8th node is shared by the 2 local residuals as I discussed. And for this case, if you want to know what are the global variables, so here it is 3 u1, u2, u3, u4, u5, u6, then 9, then 12, then 15, then you have 18, 21, and 22. So it will start from 22, 22, 23, 24, and so on. So this is the way. So these are the bookkeeping tracking of the variables. We have to bookkeeping tracking of the variables you have to do in your computer program. So we are now constructing the residuals for the corner boundary nodes. So these are the corner boundary nodes, and here is a hot wall. So dimensionless temperature equals to 1, and we can have residual for the, and also no slip boundary condition. That means capital U equal to 0. That is dimensionless velocity of x component is equal to 0. Dimensionless velocity of y component equals to 0, and that would lead to the homogeneous Dirichlet condition. So you have R11, you have R1u, R1v, and R1 theta, and for the first corner node R1, R2, R3, and this is the way your understanding. So this is the way you understand. So this will be coming from your understanding, and this will not be understood by the computer program. So computer program to write in terms of the global residual format and global variable in terms of small u. Similarly, lower right corner, that is 1, 2, 3, 4, 5. You can have the, so it will be starting from R13. Remember that global residual format, because when you give the global variables to Newton-Raphson method, it doesn't understand what is velocities, what is temperature component. It will only know the global matrix. So similarly, we will have residual for corner boundary nodes upward direction. So top left corner. So here we have Dirichlet condition. Here we have Neumann. But when you have Dirichlet and Neumann condition, Dirichlet condition is stronger boundary condition. Still, you can have the Dirichlet condition at this point. So here we can see from your calculation. So although it is 21st node, but it is 20th node, so 20 into 3 is 60. So it will be 61, 62, 63. Okay. So similarly, it is 24th node, so 72, 24 into 3 is 72, so it will be 73, 74, 75. So this is the way your calculations will be actually done. So this is the way global residuals are calculated, and we can say these boundary conditions. So next we'll be talking about internal boundary nodes. So we can have the boundaries here. So these are the Dirichlet surfaces. So these boundaries are also done in the similar manners, similar manner. And also this is the algorithm I am actually proposing. So that is 3i minus 2. So that means if we have the local node number I, say maybe 3, 4, we can with this algorithm we can get the global residual numbers. So these are all usual residuals for the Dirichlet conditions. So next we are talking for top internal boundary nodes. So top internal boundary nodes will not be that straightforward, because these are not the Dirichlet conditions. Here we have Neumann condition, that is n dot grad theta equal to 0, and you need to solve the you need to write the residual to get the algebraic equation. So this is the first time we'll be writing the residual for this case. So this is the node which is 20, 21, 22nd node. So 22nd node means it will be 3 into 21, 64, it will be 65, 66 and 67. So or you can write 3i minus 2 for the x component of velocity, y component of velocity. For them still we have the Dirichlet condition, but for the temperature you have Neumann condition. So for the temperature you need to write the residual. The residuals are u dou theta dou x plus b dou theta dou y minus dou square theta dou x square dou theta dou y square, which is orthogonal to the basis function. Here local 1, 2, 3, 4, 5, 6 is the sixth local basis function of the third element, that's written 5, 5, 6, 3, and then you do your usual calculations, and then we have another boundaries here. This is also Neumann condition, but we have this shared by two elements, as we have done in the first part of our lecture. It has to be contributed by third and fourth element. This is the basis function 1, 2, 3, 4, 5, 7, 8, 9. Ninth local basis function of the third element, and third local basis function of the fourth element. So with that, we can actually obtain the overall contribution. Then we have internal nodes. So these internal nodes are advantageous. So they are not shared by other elements. We can have only one contribution of the one element, and we can see this can be nicely structured in the computer program. Similarly, this internal so this is internal nodes for this is for the x velocity component. So you can see that is the x velocity component for the Navier-Stokes equation. So this is for the y velocity component, is the Boussinesq approximation, and these are the nonlinear terms, and this nonlinear finite element method, these nonlinear terms have to be properly handled. And you can always refer to my paper, which is Basak, Rai and Balakrishnan 2006 paper, and these algorithms are actually given for your future references. This is the temperature or energy balance residual calculation. So with that, we can one can actually obtain the generalized format of the x velocity residuals for the y velocity component, and the residuals for the temperature. These are the internal nodes, and internal nodes will also be shared here. So these are the interface nodes. These all boundary terms will be taken care. And as already shown that all internal nodes, the boundary terms will be always 0. So I'm not showing all these detailed calculations because these are all done. And then this is the node which is shared by 4 elements, and you need to have the 4 residual terms, and you get the overall compact residual for the x velocity, y velocity, and temperature for this node shared by 4 elements. So these are the velocity components in terms of the local variables, and these are the variations within the domain in terms of global variables, the local basis function, and these are basically called as global basis function. And this is the relationship between the local and global basis functions. The local basis function E is for the element, J is for local node number, and I is the global node number. So if you look at my paper, this is the format. We develop the overall global basis function with the global residual. So this is the overall residual for the velocity u, x u component balance, x y component balance, and theta balance equation, and that would give the Jacobian matrix. In this fashion, as I said, that this will be having only small u, and small u consists of velocity, x component, y component, temperature, and you solve as a overall global matrix. You do the Newton-Raphson method, as I discussed, the approximate solution vector, and then do the residual calculation and do the update. So, and here interesting part we have to I have not mentioned earlier, the evaluation of integrals we have discussed, and they are generally done by Gaussian quadrature method, and that will have tremendous advantage for the Navier-Stokes equation. If you look at what are that, if you want to know what are the advantages, you can always go back to my paper, Basak, Rai, Balakrishnan, 2006, and that paper has some of the details. And the term containing penalty parameter in the residual equations for U and V are evaluated with 2-point Gaussian quadrature, that is for the convergence purpose. Why? That is called reduced integration penalty formulation, and that is having immense importance. If you don't do, you may get some singularity in the problem, and those issues are actually discussed in Basak et al. 2006 paper. That is one of the highest cited papers. So far it is cited more than 300 times, and this is one of the benchmark papers. Many of the works, actually I can see that almost daily one citation I'll be getting from that paper, because people like to benchmark my result with their calculations. So now I will move on to the application of the finite element algorithm, what I developed. So a natural convection in enclosures, internal convection. We have worked on cylindrical. We have worked on initially square enclosure. Substantial work actually carried out. We worked. In fact, I will square enclosure. We don't have much challenge actually. It's actually easy to implement, and of course there are applications of trapezoidal enclosure. So this, you can see this kind of home design or different kind of machine parts. We have trapezoidal enclosures, and rhombic enclosures also come for if you have different kind of machine parts and or some kind of computers we have, and in between the space we need to see how's the air circulation, then rhombic results are pretty useful. Cylindrical enclosures, circular geometry, there are some calculations. We have the carved enclosures for the solar heating cases, enormous applications actually found, and this is for the solar collection system. We also have triangular enclosures. In fact, I would like to show you how to use a square element or the 4-noded elements to model the triangular cavity. So these are the applications I'm going to discuss next in my last part of my this lecture. So we have the solar energy collection systems and efficient. So these applications for efficient design in building and ventilations and thermal insulation. So again, I would like to reiterate about the governed equations for this type of problems, whatever I'm going to discuss. We have assumed a Gauss-Nest approximation. We actually applied constant physical properties except density, and no slip at the walls U and V equal to 0, and we have local thermal equilibrium within the porous medium. So the continuity equation, which is dou U by dou X plus dou V by dou Y equal to 0, we employ, and we have these are all dimensionless quantities. We have momentum balance equations. U dou X plus U V dou U dou Y. This is the convective term for the this is U dou X plus V dou U dou Y for the X component convective term. A similar convective term for the Y component. We have the pressure terms, and these are the viscous term, and this is the first time we're introducing the, because I'll be showing for the porous media, and for the porous media we have the Darcy term, and these are we have the viscous term, and sometimes some of my calculations I also have the term consisting of the Forshamer. So we have the models, so porous media models are basically done with the Darcy, Brinkman, Forshamer approximations. So so we have here alpha is of course the effective thermal diffusivity of fluid, and for porous media it is effective thermal diffusivity. Panel number we have, and we have Rayleigh number, and we have the modified Darcy number, that is the Darcy K by epsilon H square. So and of course we have the energy balance equation. No matter what is whether it's a fluid or porous media, we have the unique energy balance. We have the unique energy balance equation in terms of convective heat flow and conductive heat flow. So based on the finite element algorithm, what I discussed today for this course, in fact, these are the cases I actually simulated, and you can see all the results in the papers we have published. So the first part I am going to discuss now, uniform or distributed heating of square enclosures, and it is actually many times actually people have many applications. What they do, that they have the bottom wall hot, side walls cold, and top wall adiabatic. And what I found that in fact this problem I found in many articles. In fact, I also published, but almost like 15 years back, when or 14 years back, when a PhD student came to me, then suddenly I got into idea, because I see that when this kind of hot wall is within the nearby zone, the fluid is being heated. The top zone, it doesn't get much heat because it is quite far. So in that case, I wanted to distribute the heating in different walls. So heaters are actually distributed, and in that case, the question comes whether this distributed heating can improve the heating policy. And of course, this type of meshing actually is done by the adaptive meshing using finite element method. I'm going to address that part, and then there with that finite element simulation, we answered the question whether we could improve the heating policy for this type of problems. So next is triangular enclosure, and triangular enclosure is having enormous amount of application for the solar heating purpose. You can see that if the solar heat is radiated here, and if you have a PCM, phase change material, if you can keep a constant temperature, whether can we improve the heating with the triangular domain. We can have this kind of triangles, and sometimes what actually happens within the entrapped triangle, the fluid is actually flown, and within some of the tubes, and with this entrapped triangle, if you can have some other fluid so that you can extract heat before throwing out the effluent or pollutant fluid. So of course we have done enormous calculations of the rhombic enclosures with different excuse me, with the different boundary conditions. And then we have the carved enclosures. This has also having solar heating effects, and we have the convex side and concave side and convex side, and also we have carved enclosure for the triangular cavity. So we introduced. So basically, what actually happens that many of the works, if you look at in literature, they talk about isotherms and streamlines. Isotherm talks about temperature, streamline talks about the velocity circulation. But if you want to do thermal management, that is the hot area these days. People talk about thermal distribution, but not a single experimental tool is available to see how the heat is being transported. You can have a thermometer, or you can have optical parameter, or you can have some kind of instrument to measure temperature different places, but we cannot have a measurement like PIV for a streamline, how the temperature is actually moving, how the heat is actually moving, not temperature, how the heat is moving. So there is a numerical tool called heat line, and heat line has been implemented using finite element first time by me in the literature of science, and we found enormous application, and finite element method has been found to be indispensable to implement visualization of heat flow using heat lines. And that's the efficient way to visualize heat flow in an enclosure during natural convection heat transfer. So I would like to now describe. So stream function, people are doing a lot of approximation who are using the commercial software packages, but here is the recipe for the finite element implementation of the stream function. So the stream functions, if you want to have the definition, that is minus dou psi dou x equals to v, and dou psi dou y equals to u. And with that, we can have a Poisson type differential equation, which is dou 2 psi by dou x square plus dou 2 psi by dou y square equals to dou u dou y minus dou v dou x. And this is having subjected to the psi equals to 0 at the wall. So that means at the wall, there is no slip condition always, and in that case, we can have psi equals to 0. In that case, this entire Poisson differential equation, you can actually use the basis function concept, what we actually used for our usual FEM. Advantage is u and velocity fields will be known, and that we already got. So this is like a post-processing application of finite element method, and that will lead to the linear system or non-linear system. Doesn't matter, you can use the same Newton-Raphson method. If it's a linear system, the Newton-Raphson method will give the convergence in one iteration. So this implementation of finite element method, it is pretty fast, and it will give a robust structure of the stream function. In fact, many of our stream functions, what we do using the finite element method, using the quadratic basis function, have been benchmarked by others, and they really got their results agreed with our solutions. So this is the typical stream function, but the point is that stream function is good. Stream function can show you the multiple circulation cells. We can see how the flow is actually occurring. Now the question is, can we visualize the similar way how the heat flow is? And the answer was no for many years. And then some of the works on heat line was actually published, and that in square domain in 1980s and 1990s. And middle of the 2000, I started to look at the heat function and using finite element method. So the definition of heat function is also, you can see, it is like stream function, but we have the advection term, that is v theta and u theta, and that looks much more complicated. That makes heat function equation much more complicated compared to stream function. And stream function has advantage is that no slip condition is actually valid at the walls, but the heat flow, if you talk about, when you have adiabatic case, there is no heat flow at the wall. But when a wall is isothermal, there is always heat flow at the wall. And in that case, you cannot have no slip condition kind of thing for the heat function, and that makes cumbersome boundary condition for the heat function. So although the heat function will be having the structure of Poisson type differential equation, it will have the boundary conditions. Complicated boundary conditions can be derived by the Nusselt numbers. We'll have the point type Dirichlet condition, we will have the wall Neumann condition, and in fact this kind of system have over specified boundary condition, which will even make the people to even struggle to understand how to implement boundary condition. In fact, people are doing research on heat function, and many people don't understand much, and there are many wrong results actually have been published. And I'm now going to write a critical note on how the heat function can be implemented with the correct boundary condition. And of course, this heat function can be also implemented using finite element method. But as I said that the implementation of the heat function requires correct correct incorporation of boundary condition, and that one needs to be careful. So the square enclosure distributed heating we are discussing now for the first case, where, as I said, that we have uniform heating and we have distributed heater 0.5 and we have 0.25 and 0.25. So you can see that all the cases, if we add the heater will add up to 1. So what I wanted to see that, if we have a hot wall and cold wall, we have found that based on heat line that is not getting much heat, because that now we can see that how much indispensable heat line concept is. With that we can really do thermal management. So for energy savings, thermal management, heat lines become really indispensable. So so in that case, if you what we wanted to do, you just take 0.5 and 0.25 heater portion, so that this will try to heat neighboring zone. Even if you shift it to the center, it can actually heat this zone, it can heat this zone, it can uniformly heat. In fact, you can do it further, but what will actually happen, although the top portion will be heated, but this will not have much influence in the bottom zone. So all these concepts, what we physically having intuition, we can see the visualization of heat flow by the numerical experiment using the heat line concept. So let us discuss some of the portions. So before that, we have done some of the numerical validation I wanted to share with you. So this is the 41 by 41 mesh, 49 by 49 mesh, and 57 by 57 mesh. And this local Nusselt number we computed, and we have seen very good convergence with the mesh sizes, and we found that grid independence is established for all the complicated cases. So the validation of heat line, that is also very important. So so if you want to understand how the heat lines will look like, I will give the example. For example, you have the hot wall here, and you have cold wall. So what actually happens? The fluid will actually get heated, and it will go top, and these are bottom and top walls are adiabatic, and the fluid will go down. So in that, if the Rayleigh number is very less, the flow is very weak, and we get conduction dominant zone, and you have isotherms all vertical lines, and heat lines will be horizontal. That is, having said that, it says that heat lines are nothing but heat flux lines, and heat flux lines will be perpendicular to isotherms, and that is nicely benchmarked by a heat line concept. So heat lines are orthogonal to isotherms during conduction dominant heat transfer at low Rayleigh numbers. So the convection dominant regime, when you have convection dominant regime, what we can see that this type of structure, it is actually available in literature, Deng and Tang 2002, and this is the structure of the heat flow. This is the heat lines for the heat flow, and you can see that from the hot wall how the heat is being transported to the cold zone. Okay, and this portion is basically the convective heat transport. That means if you have any fluid, that will not heat up the other zones, but that will recirculate, and that will enhance the thermal mixing. So this is the first time the heat line. So heat line is very, very complicated when you have the convection zone, because it won't be perpendicular to isotherm, rather it will actually show you how the heat is being transported from the hot zone to cold zone. And of course, it has been benchmarked with Deng and Tang. As I told that the square cavity heat lines are also already available, but by irregular domain cavity, much of the work done by our group from 2006 onwards. So of course we have seen good agreement between present work and literature. So here I am showing for the results of distributed results for the distributed heating, and we can see that this is the streamline. I have highlighted heat lines by pi, and temperature by theta, and this work was published in International Journal of Heat and Mass Transfer and Energy, and of course some of the works have been published in INDC research. So this you can see that this are the arrangements of the distributed heaters, and these are the streamlines, and you can see when the heaters at the bottom, we can see much of this zone is very cold. You can see temperature is actually maximum 0.1 to 0.2, and this is the problem, and this kind of problem actually also occurs when you have heater at the bottom wall. And if you want to see the how heat is being distributed, you can see the heat line trajectory. Heat is being distributed here, heat is being distributed here, and some portion of the heat is actually it is going there, but very little amount of heat actually goes there. Only the cold fluid will keep circulating, and that will keep the fluid cold. So when you shift the heater slightly at the end, so some of the heat has to go at the top, and that can be obtained only from the side wall. But when you put the top at the side wall, that near the top like this, we can see this hot fluid, and it is so this hot wall is giving fluid like this heat to this direction, and this is also giving heat to this direction, and you have one uniform circulation cell. And here also you can see, so you can see different patterns of heat line trajectories, and that will give explanation how the heating phenomena is. And you can see that the temperature is being enhanced when the heater is actually center, and in fact you can see much higher circulation is observed, thermal mixing is observed when the heater is actually at the top. And we also had the further distribution of multiple discrete heater sections, and you can see a large thermal uniform mixing zone available. So these concepts are actually so the basically how we actually got into the discrete heater because of the finite element based heat line computation. It was the computation was so straightforward. With that we could easily compute and try to obtain the optimal configuration of discrete heaters. So next will be that was actually I showed for the low Prandtl number fluid, or basically typically represent the molten metal kind of fluid. This is the high Prandtl number, and this temperature is distributed. That the temperature is sorry, the Prandtl number is 1000, and which will actually which will talk about the liquid, the oils, which talks about the oil. So so you have the heat lines and stream function temperature as usual, and you can see the effect of the flow is dramatically enhanced. And here you can see, although the high high Rayleigh number is 10 to the power 5, previously was also 10 to the power 5, but for this case you can see for this configurations, even this configuration definitely high thermal mixing. So with more and more distribution of heat are definitely enhanced, but you should not distribute even more, then in that case effect will not be that much prominent. So this type of work actually was possible based on the generic finite element code and also implementation of heat line. We have, as I promised, that we discussed about the triangular cavity, and now we are talking about right angle triangular enclosure, and that boundary conditions we can have hot or cold. We also have hot or cold, adiabatic. And here I am showing the finite element mesh generation. You can see the finite element mesh. This is the mesh as can be done by mapping. So basically, the entire domain can be mapped in a square domain, and we can generate a square domain mesh generation. And once you map back, you automatically get a triangular domain. And one of the triangular elements will be focused this way, and that can be mapped locally for the integral evaluations. So this is the these are the typical calculation for the flow in porous media. This Cannon number 0.7, layer number 10 to the power 5, Darcy number -3, and we have shown the temperature, psi and pi, and in fact you can see for the heat functions how the heat functions actually more and more heat lines. Concentrated focus means high transport zone. So it can also tell us, okay, these are high heat transfer rate zone, and because of that you can see high temperature gradient. So that actually gives an idea. In fact, we can see here the temperature is not that much, fluid is not heated that much in porous media, and you can see the heat lines can't even reach there. It will be stopped here because it cannot protrude the high amount of fluid flow structure. So so in that case, that will actually give us some idea. We also need to distribute the heating. In fact, we also did enormous amount of work on distributed heating triangular cavity, and there we concentrated much on how to enhance the heating near this zone. So as here also, so we can see that how the even linearly heated left wall 1 theta equals to 1 minus y, how we can see that the effect. So so it gives an idea the how heat lines can be useful, can be indispensable to explain the level of compression of isotherms in many places. So next we have also worked on flow in hot right wall. So previously we looked about the hot left wall, next hot right wall. The similar kind of concept we found from the heat lines. This role is pretty important. And then we looked into we also calculated Nusselt number based on the finite element basis functions, and we also got the Nusselt number which can be explained based on heat lines. So based on heat lines, you can also find out for a particular wall which zones high Nusselt number, which zone we get lower Nusselt number, and based on that local Nusselt number, one can also obtain the average Nusselt number, and that average Nusselt number can also be obtained, can be calculated using the good strategy using the Simpson's one-third rule and other stuff. So this work has been published in Energy, and so I was talking about triangular cavity. So this is our domain, and also people started asking what is the application of this domain. For example, this domain actually occurs when you have this kind of diamond cross section or a square cross section, like a tilted square cross section, and you are having you can see the arrow direction, you are actually throwing some hot effluent fluid to the disposing. But people say that when you dispose hot fluid, we can take out the heat and then dispose. So that heat will be useful for some other heating purpose. And what we can do, the entrapped triangle, you can actually put some cold fluid so that fluid will be hot, and in that case that will be useful for other appliances. So this is the typical structure for the finite element mesh, and both the meshes actually map to the square domain, and for each domain we did the integration using this concept in the square domain, in the z eta square domain. So here is the we also have done the heat lines, and we have found the different kind of situations for the top and bottom triangular cavities. You can see that top triangular cavity, this zone, the high transport zone, but in the bottom triangular cavity, the horizontal portion is actually high heat transport zone. So what actually happens that we can see more thermal mixing, more effect, and here's the less thermal mixing. So in that case, we sometimes what actually happens to get more kind of circulations or more heating effect, one can think about different kind of fluid entrapped in these triangular cavities. So those kind of concepts can be available, can be obtained, can be deduced from the heat line concept, and this was actually done for porous media E8 into minus 3. So so similarly, we can one can actually have the high transport zone, high heat function gradient for the porous media calculations, and then we can then one can so we can entrap triangular enclosure porous media. We have this different kind of flow structure we obtain. We can see the top portion and bottom portion have different kind of flow structure, and that is the based on heat line concept, and this can be deduced from the our FEM calculation. Rhombic enclosures also we have done. These are meshing structure. This all the meshing program has been done based on our in-house computer program, and this is the different scale of porous, different kind of structure. We can see that different base angles, and we can see different kind of structure. And it's, of course, this pi is the heat flow structure, how the heat flow is actually occurring, and how it can be changed with the different kind of base angles. And this is for isothermal and non-isothermal heating porous media. And this is for the one is the Rayleigh-Bénard heating. It's a very interesting concept. When you have the cold, hot fluid and cold fluid, it's adiabatic. This will be the square domain people will call this Rayleigh-Bénard convection. And Rayleigh-Bénard convection can also occur for porous media, and that gives sometimes dual solution. Sometimes we get that. That means we get two solutions and or multiple solutions. This you can see that these are the stratified layers, and these are the circulations. So at the same parameter. So this can be also captured by our finite element computer code. And then next we have worked into concave and convex enclosures. So we have just see the kind of meshes. So this is the concave, the convex enclosures, and this being generated based on a generative computer program. So this is actually modeled by a parabolic surface, and then we'll have unique curve, and you can see that this entire curve domain can be mapped to the square domain. We generate all the nodes. When we map it back, automatically we get the curves. That's the beauty of our mapping configurations and the mesh structure. So this is the regular. These are the local nodes, and each nodes can be this kind of distorted element can be also mapped to the square domain for all the numerical integration purpose. So convex enclosures also similar way we can actually look into, and similar mapping is actually also possible in zeta domain. So the concave enclosures, these are the results for the heat lines. You can see that for the if you have highly concave, we have stratified layers, but for and for high Rayleigh numbers, we have seen different kind of. You can see different kind of scenarios. So concave versus convex enclosures, we also did by higher panel number and Rayleigh number, and of course that this heat line actually will give you that where is the high density of isotherms located, the high rate of heat transfer. That because this is the hot wall and cold wall, and which zone of the hot wall will be responsible for transferring heat. So we also did the work on curved triangular enclosures, so the adiabatic, cold wall and hot wall, and you can see the mesh structure here. And these are the different shape of the curved domain. And remember that all these shapes of different kind of shapes of the curved domain, the mesh generation has been done by this generic algorithm. So this algorithm is actually useful for any kind of shape. We can actually use this algorithm to generate the mesh. So next we will be talking about the another part which is called as entropy generation, because we have been working on the heat transfer, but because of any transfer process, when it works, it actually gives the entropy generation. That entropy generation will more entropy generation means less and less efficiency of the system. For example, we are driving a car in the village roads are very bad, and driver has to really struggle, and that means we have more entropy generation. When you put the same car in the main road where the highway, the road is smooth, then less entropy generation. So when you have the high temperature gradient or velocity gradient, so it looks like it has the less efficiency because more entropy generation. So entropy generation, I don't want to get into much, so this actually requires derivatives and square, and this has to be precisely computed, and this can be also done using finite element method. And you can see that how the derivatives, complicated derivatives within the complicated surface can be obtained by easily by finite element method. And we have done the benchmark of this derivative calculation for various nodes, and these are the panel number, array number parameter, and for those geometries what we have discussed, we also looked into the entropy generation part, and we can see that, and near the wall temperature entropy generation is more, and then center is not that much. So that means for distributing case, when you do distributing case, we can have more local and local entropy generation zone, and that has to be optimized. So entropy generation also talks about efficiency of the process. Today I don't have much time because I have to complete this, and these are the results for the entropy generation part we have done for different cavities, and all entropy generation was done by finite element method. And I would like to end here, and this is my another aspect of the lecture, because there are various aspects of finite element method. I have done enormous amount of work in computational electromagnetics and microwave radiation, different set of equations, complications, and but that can be also handled by finite element method. With this note, I would like to thank you all for your kind patience and attention for my lecture. Thank you very much.
Thank you very much, sir. Let the participants ask some questions. Any question from participant side?